kids. Shubhamangalam at Clinical Scholars. Myself, Sukdeep. I'll be taking class 9 for today, Physics Chapter 1. And the name of the chapter is Matter Around Us. I've mentioned the page number for your convenience over there. So we will be discussing a very important topic, that's diffusion. So here, for example, let's consider if I light up an agarbatti or an incense stick, and once I light it up, because the smoke particles of the incense stick are going to have some fragrant materials also. So the person who's sitting with me along with me or inside the same room at a certain distance is also able to smell the fragrance of the incense stick. So do you get what I mean? Similarly, if I apply some perfume or use a deodorant and I'm standing in one corner of the room, the person who's also there along with me in the same room, but at a certain distance, is also able to smell the perfume and the deodorant. So why do you think this happens? Okay, the smoke particles of the incense stick are going to mix up with the air particles, and the air carries them towards the person who's at a distance from me, but in the same room. Okay, do you understand? The same thing happens with the deodorants and perfumes also. The fragrant particles of the deodorant and perfume get mixed up with the air particles, and this is carried on with the air, and whoever is there in the room is able to smell the perfume. Okay, this is the mixing up of all these particles of the mixing up of matter particles, so that somebody is able to smell it, and so that if somebody is able to carry it forward, is one phenomena of diffusion. For example, if your mother is cooking some really good food in her kitchen, and you're able to smell, and you start guessing what is she making. So how did you guess? Because you were able to smell it. Even though you were sitting in the hall and she's making it in the kitchen, you're able to smell the smell of the food. Okay, so let's deal with it further. Okay, we are going to observe diffusion of liquids over here. For this, we are going to take a round bottom flask, and I'm going to fill it with water. In this, I'm going to add some drops of potassium permanganate. Please note it down. The formula of potassium permanganate will be KMnO4. Okay, other than this, we can also use ink or any other liquid which has a certain color. Okay, so now for example, if I'm adding potassium permanganate, to show the difference, I will show it like this. So for example, in this round bottom flask, I already had water, two-thirds of water, and in this I have added some ink, okay, or the liquid potassium permanganate. So what happens to this? It is going to get mixed up with the water, and the water turns either in purple color because of the potassium permanganate, or in blue color because of the blue ink. Do you get my point? It is nothing but in the flask I have water, and I am mixing up ink in it. For example, if I mix ink and water, what is the color of the resulting solution now? It is that of the color of the ink. If the ink color is blue, the resulting solution is going to be of blue color. Do you get my point? How did this blue color happen is the question over here. So now what happens is, potassium permanganate is actually purple in color. Okay, now the molecular arrangement of potassium permanganate liquid is going to be somewhat like this, has certain spaces. Okay, similarly, the molecular arrangement of water is also going to be somewhat like this. So when they mix up, these molecules are going to fit into the gaps present over here, and they are going to mix up together, and they form the resultant solution, which will be a purple colored solution. Do you get my point? This is called as diffusion of liquids. And how is it happening? Because these liquid particles got mixed up with the other liquid particles. And how did they get mixed up? They got fit into the spaces present between the molecules of this particular liquid, which is nothing but water over here in our case. Okay, so because of the interspatial arrangement over here, the particles got mixed up in this. For example, take some other example over here. If I was having a container, and it contains water, and in this I add 1 tablespoon of salt. Salt is solid, all of us know. If I take one tablespoon of solid, 1 tablespoon of salt, and I'm going to add it in this, and I stir it. Once I finish stirring, the resulting solution is nothing but salt water. But can you see the salt particles in them? No, because they got mixed up. You will have a faded off-white solution. That's all because it is nothing but salt plus water. How did salt get mixed into this? Because water was having molecules which have certain spaces, the salt particles got fit into the spaces which were available in the water solution, in the water molecular arrangement. Okay, so now the next one that we are going to discuss is diffusion of two gases. Here we have discussed diffusion of two liquids. One was water and the other one was ink or liquid potassium permanganate. We have also discussed how solids get diffused into liquids. What was the solid over here? It was salt, and it got diffused into liquid, which is nothing but water, giving you salt water. Do you understand? How did salt get mixed into water? Okay, it is going to mix up with water by taking up the spaces which are available in the molecular arrangement of water. Okay, so if these big molecules that you see over here are nothing but the molecules of water, the tiny particles that you see over here which got fixed into the spaces available between them is nothing but salt. Do you get my point over here? If this big molecule is water over here, the tiny particles are nothing but salt. And the resulting solution that I get over here is salt and water. This is diffusion of solids into liquids. Now we are going to study about diffusion of two gases. For this, we need a long test tube which is open at both the ends. So I'm going to take two cottons, and one of the cottons I am going to dip it in hydrochloric acid solution, and the other one I am going to dip it in ammonia solution. Okay, one cotton is dipped in hydrochloric acid solution and the other cotton is dipped in ammonia solution, and respectively I am going to fix them at both the ends. Okay, after some time, because these are certain chemicals, when they are left over left for a certain period of time, they are going to release certain fumes or certain gas particles. So hydrochloric acid, the cotton which is dipped with hydrochloric acid and is fixed at this end, and you're also going to close this with a rubber cork, remember that. And the same part happens over here also. The cotton which is dipped in ammonia is fixed on the other end of the tube, and this is also fixed up with a rubber cork. Okay, after some time, this is going to release hydrogen chloride gas and this is going to release ammonia gas. Okay, and they are going to travel at a certain length. Now, ammonia is going to travel faster because it is much lighter when compared to hydrogen chloride. And when hydrogen chloride and ammonia combine with each other, they are going to form fumes which are nothing but a composition of ammonium chloride, NH4Cl. Do you understand? HCl plus NH3 is going to give you white fumes of ammonium chloride. This is how two gases got mixed and they formed a white ring formation over here, which is nothing but a deposit of ammonium chloride. Okay? Remember, ammonia traveled faster because it is a much lighter gas when compared to hydrogen chloride. Where did you get hydrogen chloride from? Of course, hydrochloric acid. The cotton which was dipped in hydrochloric acid solution was fixed at this end, and after a certain amount of time, it started releasing gas particles of hydrogen chloride, which started traveling along the test tube. And when they meet up, they are going to form a deposit of ammonium chloride. So this is the experiment of diffusion of two gases. To sum it up, we started with diffusion of two liquids, liquid potassium permanganate and water. Then we were discussing about sodium chloride, which is nothing but salt plus water. Both of these were liquids over here. This was salt and the liquid. This was a solid and a liquid, and these are two gases. Please read the lesson, you will understand much better. Okay. So yeah, we were discussing about diffusion. Diffusion is basically a phenomena when the particles of the matter are going to mix up with the same particles of some of the same matter or with some other matter, like the gaseous particles mixing up with other gaseous particles, or else the liquid particles mixing up with the liquid particles, or the solid particles mixing up with the liquid particles. Salt plus water, the smoke of the incense stick with the air particles, both of them are gaseous in this case. So now moving forward, so we need to understand, can matter change its state? Okay, in the beginning of the lesson, we have studied that there are three states of matter: solid, liquids, and gases. Can there be an interchange or interconversion between them? Okay, we have already studied this. Now there's water, which is liquid state, which is in liquid state, and it can be converted into solid as well as gaseous state by respective cooling as well as vaporization. Now we have further examples over here. If I freeze, or I place the bottle of coconut oil into the freezer, it is going to turn into solid. Yes or no? So this is a change in state over here. Now I have camphor. Camphor is nothing but the kapuram that you're going to use in pujas and all. Okay, now this camphor, if I light them up, they are going to directly convert into gas. And this process is called as what? Sublimation. So the camphor balls are originally solid in state, and they convert into gas when they are lit up, or once you're going to add them to fire or something like that. Now naphthalene balls, be careful while adding them, of course. Naphthalene balls, so when I place the naphthalene balls in the folds of my clothes, in my almirah and all, after some days I don't see them there. Why do you think so? Okay, those were solid balls. Naphthalene balls are solid in state, but after some days when I go back and check, I don't find the naphthalene balls in my almirah or in the folds of my clothes. Why do you think this happened? Because they got vaporized, they got converted into gas. Okay, naphthalene balls are also called as mothballs. Why do you think they're called as mothballs? They keep the clothes away from insects. They prevent insects and moths, attacking your clothes. So it's a really good practice basically to keep your clothes in a safer condition, long lasting. So now what is matter made up of? Very easy. What do you think? Okay, when you look at a glass of water and you are adding a 1 teaspoon of salt in it and you mix it up and you place it in sunlight, can you see certain particles moving in them? Okay, can you come to a certain conclusion that that salt water inside the glass has tiny particles in it? Okay, so can I say matter is made up of tiny particles? Now we need to know how tiny or how small are these particles. Okay, so for this we have a simple activity over here. So what do we do is, what's the question over here? How small are the particles of matter? Again, I take a container which contains water in it, and I am going to add 1 spoon of potassium permanganate crystals. I've told you earlier what is the color of potassium permanganate. It is purple. Okay, and right now I'm going to add potassium permanganate crystals. How many crystals? Just 1 spoon of potassium permanganate crystals, which are purple in color. Remember that. Okay, when this purple crystals mix up with water, what do you think will be the color of the resulting solution? Purple. Definitely, it is going to be quite dark purple, the end resulting solution over here. Now, if I take, one test tube. Okay, for example, if I take 10 ml of this dark purple solution and I mix it up with, again, a container which already contains water. Okay, did you understand? Initially, what did I do? I have a container which contains water, and in this I am going to add 1 spoon of solid potassium permanganate crystals, which are purple in color. When this purple color crystals are mixed up with water, the resulting solution is going to be dark purple in color. What do? I take 10 ml of this dark purple solution. I take 10 ml of this dark purple solution and I pour it in a container which already contains water. Don't you think that this dark purple is going to fade out a little bit? Yes, it becomes a little light. Okay, so this is nothing but lightly colored solution, lightly colored potassium permanganate solution. Okay, let's repeat the process. So I take another test tube of 10 ml again, and I am going to take this lightly colored purple solution. Okay, here I have the lightly colored purple solution, which is 10 ml in volume, and I'm going to mix this lightly colored purple solution again in a container which already contains water. Do you think the color of this solution is going to be the same as this solution? No, it is not. It will be absolutely faded out. If I keep repeating this process one more time or two more times, the resulting solution that I'm going to get at the third or the fourth step is going to be absolutely faded out. But it will have a slight color in it. It is never going to be transparent. It is definitely going to have certain traces of the purple color solution, but lighter. Okay, initially in step 1, it was completely dark purple. In step 2, when I've taken this dark purple solution and I've mixed up with water, I found a little light colored purple solution. When I repeat the process, it is lighter than the previous one. And if I keep repeating the process, it is going to be lighter and lighter till I reach some 7th or 8th step. Okay. Even though if I reach the 5th, 6th, 7th or 8th step, a certain trace of the potassium permanganate is always going to be there inside the last container also, which is going to be absolutely light in color when compared to step number 1. So what conclusion do you come to? That the particles of matter are very tiny in size. They can end up how much ever you're going to use them. Okay, they're going to be really tiny in size, very minute and very microscopic. Okay, so by this we are proving the statement that matter is made up of tiny particles. So now we are going to learn about another point which states that there exists space between particles. So if I take a container over here which contains water and I add salt to it. Salt is solid, water is liquid. Okay. Now let's discuss the molecular arrangement of water. It is going to have certain spaces between them. So once I add salt to water, the salt particles are going to enter the space which is present between the liquid molecules. Okay. So once I add salt to it and I stir it up, do you see that the level of water has come up? No, it doesn't come up because salt has actually entered the spaces which were available for it. Do you understand? So this proves that there exists space between particles. Now, the second point that we are going to discuss over here is particles of matter attract each other. Now, okay, if I leave the tap open, there is a stream of water coming down. Okay, I can move my finger through it, but the water still continues to come down. Yes or no? I'm able to move my finger through the stream of water, but still the water is actually pouring down of the tap once I open it up. Okay, so what keeps these particles together? That is all because of the attraction between them. So there's one more point. The second one, that the second example that we are going to discuss is the iron nail. Okay, now if I take an iron nail and I try to move my finger through it, can I pass my finger through the iron nail? No, because it is a solid and the molecules inside it are tightly and compactly packed. Okay, they leave me no space. They leave me no space so that I can pass my finger through it. But that's not the case in the stream of water. When I let the tap open and the stream of water is flowing down, I'm able to move my finger freely. But I also notice that the stream continues. Once I've completely moved my finger, the stream of water still continues. Why do you think this has happened? Because of the molecular attraction in liquids. This shows that there exists a certain amount of attraction between the molecules of that particular particle. Do you understand? Whereas in solids, the attraction is so high that you cannot move your finger through the solid at all. Do you get my point over here? So we have discussed two examples over here which prove that particles of matter attract each other. Okay, now the last one. How diffusion takes place. What do you think? How does diffusion take place? Only when the particles of one matter mix up with the particles of another matter. Do you get my point? The smoke particles of the incense stick got mixed up with the air particles and the air was flowing continuously inside the room, and that is why the person at the other end of the room was able to smell the fragrance of the incense stick. So this means the particles of the matter which are going to possess diffusion, they need to move continuously. Okay, so you need to remember that the rate of diffusion of gases is much greater than liquids, and liquids have a greater rate of diffusion when compared to solids. Okay, so why do you think the rate of diffusion is the highest in gases? Because the speed of the particles is the fastest. That is one reason. And the second reason being that they have a very high intermolecular space, okay, which helps the other particles to, fit in or enter in very easily. Do you understand? The two factors because of which the rate of diffusion is the highest in gases is because of the speed and because of the space. Okay, the speed of the particles in gases is very high, and the space in the gaseous particles or the gaseous molecules is also very high, which helps in other particles to fit in very easily. That is why diffusion takes place. Okay, for example, um, we open up two containers which were containing some chemical gases. Okay, one of the chemical gases is transparent in color or colorless in color or colorless, and the second one is bromine, which is usually brownish in color. If I mix them up, what is going to be the resulting solution? What is going to be the resultant color of the gas? It is going to be brown color. Do you get my point? If I mixed up a colored gas with a colorless gas, the resultant gaseous solution or the resultant gaseous fluid is going to be colored. In our case, it will be brown because bromine is brown in color. Do you understand? Similarly with liquids also, if I pour in red ink into water, the water turns red into color, or it's blue ink, the water turns blue in color. Okay, so here the colors are much more dominating over the colorless or the transparent substances. The end solution or the end fluid is going to be colored if if one of the ingredients that you were mixing is colored and the other is colorless. Okay, please remember, if I mix up bromine with a colorless gas, it is going to form a brown colored gas because bromine is brown in color. Okay, and it gets mixed up with the colorless gas and fits or enters into the spaces which are present in the colorless gas. So that's all for the chapter over here. And yes, we have multiple choice questions also to discuss. So we will discuss it further. So the multiple choice questions are there in a textbook on page number 10. I'll read it out for you. Which of the following is available in three states in our daily life? You know this. Okay, the options are petrol, water, milk, kerosene. Of course, because water, it is present in solid, liquids, and gas. Solid state of water is ice. Liquid state of water is water itself, H2O, and the gaseous state of water is water vapor. So option B for the first one. The second one, which of the following can be easily compressed to less volume? Okay, which of the following can be easily compressed? Remember what is compression? Squeezing to a certain form to less volume. The first option that they have given is iron. Can I compress iron? Iron is a solid. There is no compressibility happening over here. B, water. Of course, you can compress water, but at certain temperature and pressure. But there are more options over here. The third one is air. Of course, you can compress air. And the fourth one is wooden piece. Am I able to compress the wooden piece? No, it is a solid. So option C is your answer. That's all for this chapter. Okay, please read the chapter properly so that you have any doubts you can come back and ask us. And yes, hope you're clear with everything. It's an easy one. Thank you.